Welcome to today's webinar, hosted by Zillits. I'm Stefan. I'm a developer advocate with Zillits, and you may know us as the company behind the leading open source vector database, Milvus, which is now managed by the Linux Foundation for AI and data science. So really excited to have here today. We have Gunnar and Gabriel from Blue Light AI. And so just a bit to give you a bit of background on our speakers. Gunnar is a co-founder of Blue Light AI and a professor of mathematics at Stanford University. And his work is at the application of mathematics of shape and form in the form of graphs, which you may know as topology, especially to the study of large and complex data sets. Gabriel is a senior data scientist at Blue Light AI, leading applications specifically into vector databases. And he developed Blue Light AI's clustering-based methodology for comparing and improving embedding models for retrieval tasks. So I'm really excited to have Gunnar and Gabriel here today. As I'm sure you're well aware, this embedding stage of the vector database pipeline is one of the most important. Really excited to hear about any ways that we can improve our embedding models. And Gunnar and Gabriel will be talking today about some technology or methods they've developed at Blue Light AI to help optimize your embedding model, specifically using these insights from topological data analysis. So really excited to learn more and think this could really just increase people's, the performance of their applications with Milvus and Zillits Cloud. So welcome again, Gunnar and Gabriel. Take it away.
Fantastic. So thank you, Stefan, for the introduction. The title of this presentation is How to Optimize Your Embedding Model, which, as Stefan said, is really a core choice in setting up your vector database. And we're going to walk through some applications of both how to best select your embedding model and how to develop it further for your use case. And our core technology is TDA.
Yeah. Hi, welcome everyone tonight, and thank you for the invitation to speak here. Stefan mentioned I'm a professor of math at Stanford, but the co-founder and CTO and president of Blue Light AI. We're taking the math that I originally worked on DARPA projects and National Science Foundation projects in the teens and 20s. And we're bringing that to bear on AI. Before initially we thought it was simply about understanding data, but it works very well for artificial intelligence. So yeah, I'll hand over to Gabriel.
Yeah, so it's a pleasure working closely with Gunnar. I'm a senior data scientist at Blue Light AI. My name is Gabriel, and I developed this methodology in the presentation for evaluating and comparing and improving embedding models. So who are we as a company? We're a company that believes in giving teams more visibility and control into their AI models. Through our approach of TDA, we found that there's a lot of value we can provide specifically for vector databases. So the agenda for this talk today, we're going to talk about the problem that we discovered, which is that there's a lot of limitations today and risks with how model evaluation is done for vector embeddings when you set up your vector database. And we're going to also talk about the solution, of course, which is a navigable clustering with topological data analysis. And what you'll see is very interpretable tables that tell you about the performance of your model. After that, we're going to walk through a specific case study we did that's published and go through different stages of the machine learning lifecycle and how we provide value there. The case study is focused on e-commerce data. So the problem. Obviously, a core choice for your vector database is in step one in this diagram is choosing your embedding model. It's what transforms your use case, your data, into a more intelligent representation that the vector database is structured to handle. And you want the best embedding model because that makes your vector database perform better, more intelligently. However, there are constraints. There's storage costs, there's speed costs. There's also a desire for visibility into how well the embedding model will perform. So just because it performs well on some benchmark, does it actually work for you? So we're going to talk through that. And we've spoken a lot to the community, and when we ask, how do you choose your embedding model for your production pipeline, we've heard some varying responses, some less than the ideal. So people are going out to leaderboards like MTEB. Some people are not very happy with, they sense that there's a lot of overfitting to those leaderboards. There's also a popularity contest for embedding models. People talk about the downloads count, and that's perhaps a sign of how popular models are and if you should trust them. There's a lot of research paper excitement and viral talk on Twitter and LinkedIn. And what we'd rather do is present you with a scientific framework for addressing how does the embedding model perform for your data, and how do you compare amongst these exciting models. So yeah, just to clarify, the embedding model is going to transform your unstructured data into something that is stored in the Zillis cloud. And whenever there's queries in production to the vector database, that embedding model is used as well. So some concepts to hold on to. Why evaluate embedding models at all? So in machine learning, there's some standard universal principles like train test mismatch, which is saying, like, just because like some great company or team publishes an embedding model that does great on an academic benchmark, we have to recognize that they trained their model often for that benchmark. And even if they didn't, there's going to be a mismatch for your use case, which is a domain specific private data often, and the data that the model was trained on. So you do want to do that testing. And also there's overfitting. So there's a lot of concerns today about public benchmarks. The data is out there, and that it's very common in machine learning that models will be published that are specifically too good at the benchmark. They've done too much training only on the benchmark. And when you apply it to new problems, new data sets, they do much worse than you hope. So on the plus side, the benefits of doing an evaluation, you get to sanity check the performance of your model. You could prevent costly mistakes. You could prevent losing potential users in production if a model doesn't perform well. And you get to confidently choose your model rather than feel like it's an ambiguous guesswork. And furthermore, the evaluations are going to help you choose the best performing model, because pushing models into production is a competitive process. You want to make sure that you get the best choice that you can get. What we've seen for choosing an embedding model for vector databases is that today, the current approach is have you look at the average performance on an entire data set. And when people are advised to look at the actual queries, we've seen in many cases that they're advised to look at individual queries. Now, each of those has its own merit. However, if you take the summary of an entire data set, you're not seeing where the problems are happening. And if you look at individual queries, how can that help you to answer what's happening in data sets that are 100,000, a million, or a billion queries? I personally was on a team that was looking at 100 queries per day, and but there were 10,000 coming in. So even data scientists have to grapple with this scale in new ways. So in the current status quo, you might end up with a table like this that summarizes, okay, here's an embedding model, for example, in embedding model 1 is a column there, and you might summarize some performance scores across an evaluation data set. And when you see a table like this, you have to remember that it's not addressing like what are the kinds of queries that are performing well or poorly. It's sort of this general health check of, is one model, vastly superior to another model? Does this model meet some like minimal threshold that you have in mind for, let's say, precision and recall? And we'd rather give you an approach that tells you more about your actual queries. So to give some more context into how evaluations work, if you were to look at a single query, for example, in our ecommerce case study, the vector database might take in a query like television stands. Somebody's looking for this kind of product, and the vector database is helping recommend products for that query. The ground truth in the evaluation could mention different kinds of TV stand products. It could be TV carts, could be TV stand 2 feet. And when you do the evaluation, it's going to be compared against these ground truth labels. So for example, here, model A incorrectly predicts black television, which is just different than a TV stand, which is what the person was looking for. So the evaluation score will reward the model that is actually getting the ground truth predicted correctly. You'll also see evaluation metrics that reward getting the right ranking of predictions correctly as well. You're probably familiar with when you go to Google search or you go to Amazon, like you're more interested in the top search results than the results on page 12. So to summarize, like the limitations with the current approaches, it's risky to trust an average across a whole data set because it doesn't tell you what kinds of queries are performing poorly in that average. And it's also not scalable to look only at individual queries to understand what's happening. So why navigable TDA clustering for these problems? It's an approach that helps you understand the performance breakdown for your embedding model on your own data set. And we've also built it out so that it makes it easy to compare models on your own data set in a very transparent and clear way. And furthermore, we've identified how to then improve your models using this information and also deploy them with more precision so you can use them when they're appropriate.
Okay, so I want to tell you a little bit about the term that Gabriel mentioned here, navigable clustering, which is part of our solution. Let me talk first of all about clustering in databases. So vector databases encode information about many things. So it takes a lot of unstructured data and vectorizes it, makes it into maybe very long vectors. But those vectors are not always that understandable. The features in there, if you've got something with 1,000 entries in the vector, they're not particularly understandable often. And so in analyzing model behavior and failure, it turns out it's very useful to cluster the points in the vector embedding. That is to say, to divide it into groups, but a number of groups which is much smaller than the collection of points in the data set. So you might take something with 1,000 points and cluster it into 5 groups. And that could be classes of queries, groups of queries, but it could also be groups of customers, that you're trying to understand. So this permits the identification of systematic groups of failure, and again, depending either on the query or on the customer. So if you have a particular customer who belongs to a group and you understand how your recommendation system or your query system behaves on that group of customers, then that's a win because you can drill down and kind of specify, understand how the system is going to work for that customer. Without clustering, you evaluate point by point or averages over the whole data set. And in both cases don't work that well. As we'll see, the average performance over a whole data set often hides the fact that there's really bad performance, locally on individual points or groups of points. And on the other hand, evaluating point by point is just not feasible. So what is clustering? Clustering divides data into groups. There are many different methods. It's been studied for the last 50, 70, 80 years. but no method, no particular method is the best in every case. And just to give you a sense of it, here's just a list of a few methods, but there's a lot of them. You might be familiar with, a k-means situation where you specify a number k and say, well, divide the data set up into k clusters for me. So what this suggests is that you need a way to do what we call navigable clustering. And what that means is you kind of have, you permit yourself, you design a collection of methods, often by using certain hyperparameters that allow you to navigate between different clusterings and to find the ones that are the best or most useful for the particular problem at hand. So let me show you, for example, here's one situation. This is a clustering of fine food reviews. So what you can see on the right there is this is a k-means analysis of that based on k-means plus a dimensionality reduction method. And what you have there is you see, yeah, there's some differentiation among the groups. There's a blue, a red, and a green. But on the left is a cobalt, which is our product, our navigable clustering product, shows you a different clustering with much sharper defined groups, and also different groups that weren't even identified in the k-means. So in fact, what you can see here is that what this clustering gives you, for example, is that there's a group like this. It's defined by a clustering, which in fact is based automatically on our network. It turns out that group is, characterized by tea, flavor, and vanilla, as you can see there in the lower right. That cluster did simply not appear in that previous, in the k-means situation. You'll notice up there too that we've got coarseness and connectivity, which are two of our navigation parameters, which you can use with a slider bar methodology. And just to give you another sense, Tisney and UMAP often produces kind of complicated what I would call hairball kind of stuff, which, as you can see here, the different groups are sort of spread throughout the entire output. So it doesn't really get down to identifying the groups in any localized fashion. So I want to give you a little bit of a sense of why it is, or what it is that the kind of problems that we believe we come up with. So, so I'm going to take you through sort of an idealized example here. So initially I'm going to say, suppose that our data consists of locations in the United States parameterized by latitude and longitude. And if you think about it, just roughly, you say, well, the natural clustering would divide the US into 4 groups, namely points in the mainland, in Alaska, maybe points in Hawaii, and points in Puerto Rico. On the other hand, if you think a little bit more closely about it, you realize this isn't quite right. The Aleutians in Alaska, for example, those islands might form clusters, and some of the other offshore islands there. Hawaii consists of several islands, 8 to be clear. So maybe one wants that clustering. Well, it depends. Do you want that one, or do you want the higher level one? That's a question that it is dependent on your use case, or on what it is that you want to do with the clustering. A second point is sometimes the question might be how important, how big, or how concentrated are particular clusters. So there are other questions beyond resolution that come up. So the previous thing that I showed you is a matter of resolution. Higher resolution would show you, smaller islands in Hawaii and Alaska. Lower resolution would ignore those questions. But there are other questions beyond the resolution that come up. For example, deciding what groupings are large enough or significant enough to include. So, for example, do we include, in this cluster in Bird Rock off the Northern California coast where we are here, this island has no people on it. It's of no real significance, but, at the very finest resolution level, it would show up as a cluster. Okay, but now, so we've taken this idealized example where we are studying points in the United States. But suppose that we don't, and measuring them by latitude, longitude. But suppose that we're interested in something other than latitude, longitude. So we might, for example, cluster by political preferences. And if that happens, as we've kind of seen, this clustering would probably contain two clusters, one red and one blue. And these are states that are characterized by their political preferences. So that's two clusters. That's informative. But what might be more informative is to use latitude, longitude, as well as political preferences. And so what happens then is you get this kind of picture. You can see here that we're not just going to cluster with two groups, but what we're going to get is we're going to get regions with political affinity to each other. So you can see here we get Hawaii, we get the West Coast, we get kind of the blue mountain states, and industrial upper Midwest, and the upper East Coast. And that's informative. We kind of believe that the politics in these places are not identical. So, you know, the blue states in the upper Midwest might be quite different from Hawaii, even though they both show up as blue and they show up as being localized differently. Now, and this is, now I want to talk about what's really relevant to the case study that we're going to show you here in a minute. So oftentimes we're interested in optimization or in finding things where places where certain quantities are maximized or optimized. So, and you know, if you think from the math side, often when you're doing optimization, you find that there's more than one local max or min. And what that means is that we kind of want to understand the landscape, not just the absolute max or min. And local optima can be very important. So in this case, we're going to show you a map of the US again, this time with occurrences of death from pancreatic cancer together with their placement, the local optima or hotspots. So here is the map of the US, and the states are colored by death rate per 100,000 population from pancreatic cancer. And you can see there's a spread, but you can see there's several red groupings there on the in the eastern part of the country. So you can see there's Maine, Vermont, there's Michigan, there's Pennsylvania, West Virginia, and Mississippi. So there are different groups here, and it might very well be that the occurrence, say in Michigan, maybe is much bigger than that in Mississippi. But nevertheless, we want to understand about Mississippi because Mississippi is elevated relative to the people, to the areas around it. And so we really do want to understand this landscape. So again, there are probably different reasons for these various hotspots. For example, presence of heavy industry in Michigan might explain their high value, but there could be likely other explanations in Maine and Mississippi. When we want to take actions, we need to know this kind of information. It's not enough to simply optimize and find, you know, the highest point. We really want to understand the different areas, different parts of our data set, which are where things are elevated, you know, or, you know, exceedingly low. And so for us, what we're going to be talking about in our case study is exactly finding these kind of hotspots where models underperform, where the Gen AI models underperform. So questions, what do we need to create this kind of clustering? We need some kind of a map, not an actual geographic map, but some kind of other map in the form of a graph, analogous to that lat-long map for the US. And we use that map and produce heat maps and cluster it, based on that map instead of the map on the US. So this is what we do at Blue Light AI for all kinds of data. We produce an appropriate map, even for unstructured data, and allow you to construct these heat maps and clusterings. We call it navigable clustering in that the construction of the map can be varied in various ways, including resolution, but you know, others as well that produce better maps from the point of view of creating local maxima and minima, finding good, you know, solid ones, and also from interpretability. So navigable clustering is part of the TDA, Topological Data Analysis, which we developed in the, you know, 10, 15 years ago and continuing, you know, at Stanford and at other universities around the country. So now what I'll do, oh yeah, one important point about producing these maps is that when you build clusterings, it might very well be that, it's an interesting question to ask. Given one group, what are the nearby things? What are the things that are similar? And that's something that ordinary clustering does not give you. Ordinary clustering simply divides things into groups. And here, what we're doing is we're going to divide you into groups. We're going to tell you what other groups are like it. And so, for example, in a group with a group label on the left there, which says, food wars in the UK, we have 3 different groups that are nearby. One is involving burgers, taste, another is involving Asian food, another is involving Thanksgiving and breakfast. So, so this kind of gives you a conceptual idea of what your clusters are doing when there are clusters that are related to each other. And that also is really important for gaining insights, and in particular, producing explanations for clusters. So what I'll hand over to Gabriel again here for the case study.
Fantastic. Thank you, Gunnar. So Gunnar has laid out the theoretical foundation for what we do. And our software toolkit basically can take in any machine learning models or data sets and do this automated analysis. So we're going to walk you through a case study specifically designed for vector databases, and the particular data set is ecommerce. So this data set is from open source by Marco. It's called Marco GS 10 million. In their examples, they work a lot with this 100,000 sample subset. And this data set is constructed of queries to Google Shopping, as well as ground truth products. So, for example, a query in this data set might be television stands. Someone is looking for television stand products. We talked a bit earlier about how there's some ground truth information about what are reasonable outputs if someone looked that up. And the performance metrics, when you use case study data like this, are going to reward both the presence of correct answers and also the rank. So we talked a bit earlier how if you looked at a single query and you wanted to understand why the performance score was the value that it took, a performance score, for example, will be higher when it's rewarding correct predictions. So here, model B gets more correct predictions. So it's just a general notion. It had a higher score than model A, which incorrectly predicted an irrelevant product for this goal. So now an exciting example to lead into. Here's what happened when we applied navigable clustering to this case study data set. So in a matter of minutes, we surfaced groups of queries that the navigable clustering found. And also we were able to sort the table to find the ones with the weakest performing scores. So this is very related to the heat map concept that Gunnar was talking about. Now, what you're seeing here is providing novel information to the current frameworks people have access to today. Using the tools and approaches from today for vector databases and embedding models, you might get some average information across this entire data set of 100,000 queries. You might come across the information that the average performance score here was 0.34. So that's what happened. The performance metric in this example is NDCG. Now, when we ran the navigable clustering, we were able to easily get a table like this that showed us that pajama products had a really low score of 0.1, which is way below the average. And as espresso machine queries also performed way, way below average. And this is going to be really important for production scenarios where you do care about the performance, you do care about weak performing cases. So we're going to talk a bit about how to interpret these tables. The left column in the table called name, that is composed of keywords that are in the cluster of queries that we found. And furthermore, they're selected based on what makes that cluster of queries distinct from the neighbors around it. So Gunnar talked about the theoretical foundations of TDA and how we have this structure about neighbors and data, and we take advantage of that information to give useful automated summaries of what is in each cluster. So rather than having to navigate like a complex visual, which is a common approach out there, and going point by point to try to form a theory of what is in a cluster, here we can give you an automated set of keywords that very quickly tells you, oh, like espresso queries are the ones that are performing really poorly. So this screenshot, what it actually is in Python is a pandas data frame, which is something that is kind of this universal tool for data scientists, universal Python package. And it behaves like a spreadsheet. So this is something that if you're comfortable with pandas data frames, you could play with it in Python there. You could also have this exported to Excel. And navigation of this table is very easy, just like Google Sheets or Excel. So you can quickly sort the table by the performance. You could filter it by a certain minimum size of the cluster if you want. You could search the name column as well. And because we made the navigation easy in a table rather than like an abstract visual, we were able to quickly get to this information that all these groups of queries perform way below average for the model. So we're going to pose a question. So what if you trusted a popular model out there from Hugging Face or Twitter and didn't do an evaluation of your data set? In this case, like if an e-commerce company used an E5 model, which is a reasonable popular choice of model to start out with, not until they deployed to production would there be like maybe they would start to get awareness over time that espresso machine queries are performing poorly. But with this evaluation approach, they could actually detect it ahead of time and take action instead of deploying a model that is clearly going to perform poorly on those kinds of queries. Other things that the navigable clustering gives you access to. So we talked about how the heat map helps you to focus on what's important to you in the data set. In this case here, we sorted for like what were genuinely the lowest scores, regardless of the size of the cluster. So here the clusters are smaller, but it's still important to know that, look, like kitchen spices and boys sweaters perform close to 0. And so if those were customers using an e-commerce site and the recommendations were close to like 0 relevancy, that could have a lot of consequences. And so a lot of teams, they're familiar with like the long tail distribution and how you do want to care about these like smaller case scenarios, because in aggregate, it could have a lot of consequences to your business if you don't support these users. We're going to talk about the next phase of the machine learning lifecycle and how this framework helps you. So we've shown you evaluating a single model, which was E5. Now we're going to show you how this table helps you to easily compare across models. So in our published case study on this e-commerce data set, the average performance of E5 was pretty good, like better than the expert model we also evaluated, like a comparison of 0.34 versus 0.26 for this metric. However, the navigable clustering surfaced a lot of groups that actually performed better in the expert model. And this opens some opportunities, like, do you want to do model routing? Do you care more about these groups that perform better in expert? Maybe they're more expensive or more popular products. Maybe they're products that are important to sell in season right now. By surfacing the groups of queries, you're able to take action, ask these questions about what's important to you in the data set. Another scenario we're going to pose to you that we've heard a lot about in the community is about saving storage costs and switching from a larger model to a smaller model. And we recognize that saving storage costs is very important, but it's also important to foresee what are the consequences of doing that. So this is a synthetic example, but the point it's driving across is as you change from one model to another, or you're considering doing so, you do want to find out not just the drop in average performance, but what kinds of queries could get much worse, because maybe that's a no-go for you if some important groups of queries are no longer supported. So here we see that cufflinks and cushions could do significantly worse. Next part of the machine learning lifecycle that people care a lot about is fine tuning. So actually like improving their embedding model. So this is a real example from the case study where we used a popular e-commerce fine tuning algorithm, and we took the E5 model from a 0.35 performance on the data set to 0.45. The maximum is 1, the minimum is 0. And we found many clusters of queries that got much worse from the fine-tuning process. So despite this average improvement from fine-tuning, these groups got worse. And that has consequences if you're going to deploy your model. But it's also an opportunity. So by becoming aware of what's happening, you can intervene. So it's possible that this fine-tuning run was a bit of bad luck. Maybe you need to change your hyperparameters. Maybe also that group of queries that is stagnating or getting worse has mislabeled data or needs more data examples to help the fine-tuning algorithm. So here, for example, we tracked a group that was hoodies based. So that's over there in the title. It says that hoodies and novelty hoodies was in a group of queries. And we're tracking several different performance metrics during the evaluation while fine-tuning from epoch 1 to epoch 14 ended up being the checkpoint that was best as we went to like epoch 25. And what we saw for this group, for example, is that there was just an absolute stagnation rather than an improvement happening. And what you saw before was that there are many groups that simply got worse. Next part of the life cycle is post-deployment. So we had identified in this case study, in this data set, for example, that espresso machine queries performed very poorly. And we surfaced that information, and that told us something novel that the average performance across the whole data set did not. Now, in production, models don't operate in isolation. They operate within your business model. And in your business model, you might be spending money promoting certain products through marketing. Now, if you knew in advance that customers would have a bad experience if they're searching espresso-related queries, then maybe it's time to prioritize other things in the meantime while you're trying to improve this experience here. Other choices you can make once you become aware about where the performance is and is not is that you can choose to support other systems to complement your embedding model system. So if you know this espresso machine experience is not going to work well in the embedding model right now, there are more like manual approaches you could set up to fix the output that you want your users to see. There's also cases where perhaps your vector database is supporting a chatbot. If you know in advance that certain kinds of queries are going to perform poorly because of this kind of evaluation, you could route the espresso queries to a human in the loop in the chatbot. We're going to go through some specifics about how this would work with the vector database as a ecosystem. So in terms of a workflow you might consider, you may start with some public leaderboards to get a sense of relevant models that are out there. And that could help you to narrow down ones that meet your size and speed and cost constraints. You could start with an evaluation of average performance to give you a sense of, some of the better models from some of the worst. However, the step 3 is really important, which is the navigable clustering we've shown you today, which helps you to understand the actual pros and cons on your data set of any model. And once you become aware of those pros and cons, you could then choose the best model for you, fine tune with more precision, and also use your models with more precision. In terms of actual data to do this kind of analysis, we use like standard evaluation data that people are using, can pass in easily to the Python framework, for example, structured as a pandas data frame. If that information isn't calculated yet, there's a couple of frameworks that we've put out notebooks to help people with. So for example, Bear and PyTrek eval help people to evaluate models on their data. And if for example, ground truth data and doing evaluation is not something that's accessible in the near future, you can still do TDA clustering to get groups on your data. So some metrics that are popular, and this framework supports really any metric that you've saved information about. And some ones we come across for vector databases, precision and recall. There's also ones related to the quality of ranked outputs like NDCG. You can also pass in live user behavior data as an indicator of performance. So click-through rate and purchase rate tells you a lot about your queries. To show you a visual example, at the screenshot below is a pandas data frame. It looks like a spreadsheet. What we're showing you is each row contains a query to your vector database for which the evaluations has rewarded it with a certain score. For example, these scores are between 0 and 1, and we're showing you like 5 different metrics just as an example here. In standard evaluations, you need at least 1 score per query. You could have multiple. Here's like an input output example. At the top is what we're talking about, which is you come into navigable clustering with at least 1 score per query. For example, here we show NDCG as the score. Row 1 could be kitchen scissors and the score could be 0.44. And the output that navigable clustering can help you get pretty quickly, and honestly a matter of minutes, is different rows containing the clusters of queries. And that tells you how many queries are in that cluster, what is the interpretable keywords for it, and we summarize for you an average over that cluster to tell you what's inside. Another example here, if you pass in this information for multiple models, we can help you build a table. For example, in the table below, we compared SBERT to E5, and we quickly summarized what the best model was and by how much. So because we were able to use a table, we're able to easily construct this model comparison on your data set. And if you're watching the recording later, feel free to pause the video and look at it deeper to get a sense of it. If you don't have evaluation scores, so we're talking about how clustering can still illuminate what kinds of queries are in your data set, that helps you understand what to prepare for and what could happen. Here, for example, from the case study, lots of groups of queries, wigs, visors, how many there were. Also, if you don't have evaluation scores for your own data set, there are evaluation scores on public data sets. So if you're choosing an embedding model that's been publicly evaluated, those public evaluations and the data used for them could be passed into navigable clustering. And that could help you to foresee some important scenarios. So for example, if you were building a legal chatbot and you don't have that kind of evaluation information for your own data set, it's very likely there's lots of good models out there that have been evaluated. You could do navigable clustering on those, and perhaps you'll surface that the model that's good on a public data set is not good at DUI cases. And so if somebody asks your legal chatbot about DUI, perhaps you should route that to a human expert instead. So some concluding thoughts, perhaps a visual to hold on to, is that looking only at the average performance on a data set doesn't illuminate the actual groups of queries that are not doing well. For example, in our case study, the average performance was 0.34, while here we see many groups of queries that performed far worse. For example, espresso machine queries, here we see 30 and performance is 0.11. And navigable clustering brought to your attention, here are the critical and actionable performance problems in your data set. And in a high-level summary, so why navigable TDA clustering? It gives you this performance breakdown on any embedding model on your own data set. Because we have a table, it makes it easy to compare models on those clusters. And then with precision, this helps you to improve your models and deploy them with more exactness. Some resources. So we have, I checked in yesterday, it looks like over 1,000 people have been trying this out. We're on GitHub, and we've got a Slack community, and feel free to reach out to us with questions and engage with us on and examples and whatever you're curious about. So I'm gonna pass it over to Stefan.
Fantastic. Yeah, thanks so much, Gabriel and Gunnar. That's really interesting. Some definitely some new ideas and concepts to me. So really curious to delve a bit deeper. Before, I got a few questions myself before we asked the attendees. So I wanted to ask, like, what's something sort of like like surprising or unusual that you found with this framework? Has like anything sort of like surprised you in applying these tools during the analysis? Oh, Gabriel, do you want to turn your microphone on? Oh, can you guys hear me? Gabriel, are you there? Oh, geez. So bear with us. We're just sorting out some tech challenges. Um,
7, we had an issue with Gunner's microphone, but I connected on my computer. Feel free to repeat whatever one of the questions might have been.
yeah, sure. So I wanted to start off with a question myself. What's like the most sort of like surprising or unusual thing you found using these tools to do this sort of like novel analysis?
Yeah, absolutely. So coming into it, I was pretty surprised that fine tuning that many groups could get worse on that case study data set.
Mm.
Very large percentage got worse, like 30-40%. And by doing the group analysis, it surfaced like, okay, like very relatable, interpretable queries are getting worse, like espresso machines. As a coffee drinker myself, I would hate to have a bad search experience trying to buy coffee related products. Another thing there is in the e-commerce case, like each visual query could be pretty valuable. So you can think like a single query could be a product worth $20. So that could be of concern.
Totally, yeah. And as like also a fellow espresso drinker, that's a subset of queries that I also care a lot about. So just sort of like delving deeper on that line. So I presume you're talking about like fine-tuning the embedding model. Have you also looked at the implications of fine-tuning the query embedding model or like the retrieval model? So perhaps you're sort of you're sort of taking like a general purpose embedding model, but then you do some fine tuning on the retrieval side. Have you found anything like interesting on that side? Maybe sort of the relative merits of fine tuning your embedding versus your retrieval model.
We have stuff, and we've done some work with a RAG situation. And there, what you can do is you can take the documents that you've got, or the ones that respond to a particular query. Say the query is, tell me about the draft. And what the clustering does is it gives you 2 points of relevance. One is the NBA draft, and the other is the military draft. So indeed, yes, that's one of the key interesting things that we're looking at.
Awesome, fantastic. Well, I don't want to monopolize all the question time. I want to hand it over to the audience. So firstly, just what's been posted in the chat. So to Darmel, so yes, don't worry, the full recording will be posted later along with the slides. So if you missed out the first bit, not to worry, or if you want to review any bits later, you'll have access to that. Okay, so we've got a question from Ed. And by the way, don't forget to click to everyone rather than just to host and panelists, so we can all see your question. But Ed has posted, do you use TDA here only for clustering? Do you have quantitative comparison of TDA clustering with HTTP scan or other clustering algorithms on top of embedding space values?
That question. So I think that one of the core things is that you don't just need the clustering, you also need summarizing keywords. So for us to do that comparison, we'd have to rebuild an entire software system. that takes not just the clustering, but the keyword algorithm, the data engineering. So in terms of, do you want kind of results today to work with? I'd recommend trying out the Python package. In terms of going back to the theoretical foundations of TDA versus HDB scan or things like that, maybe Gunnar can talk a bit about how TDA retains like more structure about the data.
Yeah, I mean, the main point is that it gives you the flexibility. So, DB scan is one method. And, it operates on that map that we, that your data comes with, or it operates on your data directly. But what the map allows you to do is to say, actually, I have this thing in mind where I'm doing clustering, but I want to do it to find, local minima, for example. That is a complicated problem. It's sort of a choice of many different thresholds all over and so we give you a simple way to navigate with slider bars that map. And so any particular method of clustering, or at least of graph clustering, could be applied in those situations, but varying the map is important, just like people thought of varying the map back in the old days when they were building geographic maps. They had different projections. So that is what we permit, and it allows you to get at your problem much more easily.
Thanks, guys. Do we have any more questions from the audience? Otherwise, I'll jump in with one of my own questions. So, if you got any questions, feel free to write them in the chat. So something I've been wondering myself. So, just sort of like following the latest research in foundational models, embedding models, etc. I've seen that a recent direction is not just learning to fine tune, but actually making your embedding model a function of the query. So rather than just sort of like fine tuning on a certain data set, you sort of, in some sense, like sort of amortize over like sort of fine tuning over all sorts of different queries. Is this sort of like a modeling paradigm you've looked into evaluating? Or is it, yeah, take it away.
Yeah, I think an answer to that is, one of the things that we didn't mention here is, but that the map model also provides a method for feature generation, and so you can actually add additional features, based on the clustering and so on, and that is, that'll give you better fine tuning. But I think it can also, address the questions that you're talking about here. So, in particular, I think. One can view it also as a part of nonlinear dimensionality reduction, and specifically directed for studying these complicated foundational models. What we've found, by the way, we've worked on the sparse autoencoder features coming out of OpenAI and others, and we find that these models give very, very interesting descriptions of the feature sets that come out of those.
Yeah, no, that's really interesting work. I'm familiar with that too. So, could you maybe just like elaborate a bit? So, what sort of like interesting findings did you have like working with these sparse autoencoder features?
Yeah. So the main thing that comes out is, so each feature, OpenAI say produces a lot of words that come out of it. But what it doesn't show is how different clusters relate to each other. So, for example, we had something which was said, this particular question deals with rules, and then there was sort of a split in how do you comply with the rules and how do you break the rules. So, and those showed up at different areas, or I should say, along progressions in your graphical model.
That's really interesting. So looks like we've got a couple of minutes left. So I wanted to hand it back to you guys, Gunnar, Gabriel. Do you have like a call to action? So, people, you got them excited about this new technology, new method. How should they get started? What's sort of a good place to begin?
Yeah, absolutely. So our Python package is called Cobalt-AI. So you could do pip install Cobalt-AI. You can also look up our company. So we're Blue Light AI. We have a GitHub package. In the recording of the webinar, there's that slide of the resources to reach out to us, our community, where our GitHub package is. We can see here in the chat that Chloe is posting some resources for setup of the software. And we're very happy to help people out with setting it up, understanding what's happening. Fundamentally, we can process huge streams of data and very quickly give you that sense of what are the clusters there, what is the performance, what is the best embedding model for you.
Awesome. Yeah, fantastic. Thanks so much, guys. I think it's really interesting so there's a lot of companies sort of doing very a lot of the similar stuff, but it seems like you guys are doing something very, very different and very, very novel, and that's what I find exciting. So looking forward to giving this more of a try out myself, exploring like how I can enhance people's applications with Milvus and RAG, etc. Yeah, looking forward to getting to know you guys better and exploring more. So thanks everyone for attending the webinar. As mentioned, we'll make the video recording and the slides available offline, and we'll follow up in an email after this. So thanks again, guys, and cheers.
Thank you.
Thank you very much.
Okay, take care, everyone. Okay, bye.